Plug a cable into a port, watch the LEDs light up, and you might assume they're ready to talk. But physical connectivity doesn't guarantee communication. The copper wire or fiber optic strand only transmits raw electrical or light energy. Without agreed-upon rules, that energy is just meaningless noise to the receiving device. To build a communication system, you need three elements: a message source, a destination, and a channel. First, the source initiates a data transfer. Second, the destination catches and interprets it. Finally, the channel provides the pathway. For these three physical elements to successfully exchange data, they require a strict set of operating agreements, known as a protocol. In human conversation, we rely on shared language, grammar, and greeting customs to understand one another. Network protocols serve the same function for computers, but require absolute mathematical rigidity to execute. Protocols are the foundational architecture of network communication. As shown in this overview, every robust protocol must satisfy 5 specific physical and timing requirements to function correctly. The first logistical hurdle in building a protocol is translation. How does a human-readable digital file actually become transmittable physical energy on a wire? Our first requirement is message encoding, mapped here from its digital form through transmission and back. Encoding translates digital data into a physical format, ones and zeros into electrical pulses or light flashes. Decoding at the destination reverses this back into digital data. With the encoded signal traversing the wire, a new problem arises. How does the receiving device know where the message starts, stops, or who it is actually intended for? This brings us to the second requirement: message formatting and encapsulation. This diagram uses a postal letter to demonstrate the concept. Encapsulation is the act of placing a raw data payload, the letter, inside a specific structural format, the envelope, to prepare it for delivery. In networking, this digital envelope is created by appending protocol headers and trailers to the raw data. These additions contain vital routing instructions. Without encapsulation, a packet is just blind data. The header provides mandatory source and destination addresses the network relies on to deliver it correctly. If a node tries to send an entire massive file as one continuous, unbroken stream of encoded data, it introduces severe physical limitations to the network medium. We solve this with message size. A single block message is highly inefficient to transmit. It monopolizes the channel, and a single error forces a complete restart. To prevent this, protocols force large payloads to be broken down into smaller, uniformly sized packets. Even with properly sized packets, another issue remains. A high-end server can easily transmit those packets faster than a low-end client device can process them. Our fourth rule is message timing, using 3 mechanisms. First, flow control manages transmission rates to prevent overwhelming the receiver. Second, response timeout establishes how long to wait for an acknowledgement before resending. Third, access method prevents data collisions on shared channels. Message size and timing rules work together to prevent network congestion. They ensure that the physical limitations of the hardware do not degrade the data payload. We now have a perfectly formatted, correctly sized, and well-timed packet. The final variable is determining exactly who the intended recipient is. This leads to the 5th requirement: message delivery options. Protocols must define the audience scope for any given transmission, starting with the most basic point-to-point communication. Unicast is a message delivered to a single specific device. Multicast delivers a message to a selected subset of devices. Finally, broadcast forcefully delivers a message to absolutely every device active on the local network. Implementing these 3 delivery methods allows networks to scale efficiently. It ensures that devices only spend processing power on the specific traffic they are meant to receive. We started with a blank slate, 2 computers connected by a single silent cable. By implementing strict rules for encoding, encapsulation, sizing, timing, and delivery, we constructed a fully functional protocol capable of reliable data transfer. But real-world networks expand far beyond 2 end devices. A single transmission might traverse dozens of intermediary switches, routers, and firewalls before reaching its destination. This introduces a critical law of interoperability. Every single intermediary device along that physical path must speak the exact same protocol to forward the message. If a router receives a packet but lacks the programming to parse its specific encapsulated header, it will instantly drop that data. To guarantee end-to-end communication, engineers rely on protocol suites, such as TCP/IP. These are bundled collections of standardized rules designed to work together in harmony. Adhering to an industry-standard suite allows hardware from completely different manufacturers to communicate flawlessly right out of the box. Protocols form the invisible, mathematical foundation of the Internet. They are the essential architecture that turns a massive web of raw physical connections into a reliable global communication system.